This is a video recording for the poster presentation. RobusTAD nonparametric test detects hierarchical topologically associating domain at the Great Lakes Mathematics Conference. I'm Yanlin Zhang, a PhD candidate at McGill University. I performed this research with Dr. Laura Daly under the supervision of Professor Matthew Blanchett. In the past decade, we have realized that topologically associated domains are basic units of the 3D genome organization. They play essential roles in many different cell functions. As more and more high-C datasets become available, we now realize that TADs are hierarchically organized inside the nuclei. However, tools to identify such hierarchy from a typical carried high-C dataset are still limited. While TADs are relatively well conserved across cells, few approaches have taken advantages of this fact to improve TAD annotation. In our recent studies, we demonstrated that we can improve loop and TAD annotations and content map enhancement by introducing additional high-C dataset as a reference panel. In this project, we aim to detect TAD hierarchies and incorporating additional high-C content maps to refine domain boundaries detected from the study sample. Our new tool, RobusTAD, can efficiently utilize a much larger reference panel than our previous tool, RefHiC. We find RobusTAD outperforms existing tools under different settings. We have two key contributions in this project. First, we propose a genomic distance stratified rank sum test to score domains and boundaries. Second, and more important, we take boundary annotations from additional dataset into consideration to improve the boundary detection for a study sample. Our RobusTAD takes a normalized high-C content map as input. It annotates TADs in 3 steps. We call the first step the study sample-based boundary annotation. It is similar to many one-dimensional score-based approach. We detect boundaries as local maxima in scores. We compute left and right boundaries separately. To compute the boundary scores for a given precision, we performed a rank sum test on their integration frequency inside TAD and across the domain boundary. As genomic distance contribute to the integration frequency, we performed a stratified version of the rank sum test. After identifying TAD boundary, we can proceed to the second step, the reference panel-based TAD boundary refinement. We have a reference panel that contains boundary scores for a large collection of high-C datasets. To refine a given boundary annotation at the study sample, we select all reference samples that also have a TAD annotation around the given precision. We believe these annotations refer to the same location. We compute the refined boundary score for this small region as the mean of scores from all samples. The refined boundary annotations is the local maxima of the mean. In the end, we will have a list of left and right boundary annotations. The last part shows how to pair left and right boundaries to form a TAD hierarchy. To solve this problem efficiently, it is safe to assume that partially overlapped TADs are not allowed. So let's say we have a given region containing left and right boundaries. The optimal TAD hierarchy can be divided into 2 parts. The TAD pairing in each part is also optimal. Thus, if we can define the score function with the proposed rank sum test, we can use dynamic programming to find the optimal hierarchy efficiently. Now we use existing scripts to compare RobusTAD with alternative tools at 5 kb. These are examples of TAD annotations predicted from the 5 kb high-C content maps by RobusTAD and other tools. It is clear that RobusTAD and several other tools can detect nested TADs, but RobusTAD made more correct annotations. Here we focus on the quantitative comparison of TAD colors. We are more confident to draw conclusions from this than from the visual comparison we saw previously. The number of TADs and the size of TADs varies from TAD color to TAD color. This is because many tools have their own criteria to select TADs, but there are many TADs that have been identified by multiple tools. It's impossible to evaluate the accuracy and the recall on real high-C dataset because we don't have the ground truth. Here we use different indirect ways to evaluate tag caller's accuracy. For example, the correlation with CT-set binding set under the beam interaction frequency within TAD. Although RobusTAD is not the best tool in most settings, taking all evaluation together, we can still conclude that RobusTAD is the best tool because it is always among the top 3 callers. Last, we saw how RobusTAD performs in handling low carries high-C dataset. As we can see, with the decreasing in valid rate pairs, the number of TAD predicted by most tools also decrease. This is a good sign because it indicates that most tools is able to maintain a low false discovery rate. We compare TAD and boundary annotations to predictions from the full carries dataset. We can see RobusTAD and several other tools are very consistent across sequence depths. The last row shows that RobusTAD can detect more TADs that are supported by CT-self loops than alternative tools. Last, I want to take this opportunity to thank Dr. Yueli and Dr. Yasik for providing useful suggestions for this project. And this project is supported by Genome Quebec and Genome Canada research grant to Professor Mathieu Blancel, and I was supported by the FR20 doctoral study scholarship. Thanks.